In this video, we're going to cover section 1.3.2 on determining reaction orders. Let's consider the following reaction, where we have two reactants A and B giving us a product C with a particular rate constant K. Now, experimentally, we may find that the rate law expression for this reaction follows this particular form, where we have the overall rate of the reaction equal to the product of three terms: the rate constant, the concentration of A, and the concentration of B. Now, a question we must ask ourselves is, how does one determine the order of the reaction with respect to A and B? How do we determine alpha and beta? Well, in order to do that, we must determine the reaction order by measuring the reaction rate under various concentrations of those two species. Now, a second question would be, what set of concentrations should we use to determine the reaction rate? Well, typically the method that is used is referred to as the isolation method, in which the concentrations of all the reactants, except for one, are present in large excess. So under these conditions, only the concentration of one species will vary to any significant extent during the course of the reaction, whereas the concentrations of the species that are present in excess, they'll remain essentially the same during the entire reaction. This time independence simplifies the rate law expression. So let's look at that. Now, using the isolation method, the reaction rate will only depend on the concentration of the species not in excess. So if we look to our previous example, if A is in excess, then our rate law expression will simplify to the following. We'll have the overall rate of the reaction equal to a new rate constant we refer to as K prime times the concentration of B to the power beta, where K prime is equal to the rate constant for this reaction multiplied by the concentration of A to alpha. Now, using this method, this isolation results in the dependence of the reaction rate on B exclusively, and the reaction order with respect to B is determined by measuring the reaction rate as we vary the concentration of B. Similarly, this method can be used to determine alpha by performing measurements with B in excess. So in that particular scenario, the overall rate would be equal to K prime times the concentration of A to the power alpha, where K prime is equal to K times the concentration of B to the power beta. So we can carry out this isolation method for both species. We can first determine the rate of the reaction with respect to various concentrations of B by ensuring that the concentration of A is in excess. And then we can carry out the same set of experiments, but now we ensure that B is in excess so that the rate of the reaction is solely dependent upon how the rate changes with respect to the concentration of A. So that's the isolation method, and one method that we can use to determine the partial orders with respect to various reactants in a reacting system, and as a result, determining the overall order of the reaction. A second strategy used to determine reaction rates is the method of initial rates. In this approach, the concentration of a single reactant is changed while holding all of the other concentrations constant, and then the initial rate of the reaction is determined. The variation in the initial rate as a function of concentration is then analyzed to determine the order of the reaction with respect to the reactant that is varied. So let's consider the previous reaction where two reactants A and B give us a product C. To determine the order of the reaction for each reactant, the reaction rate is measured as the concentration of A is varied and the concentration of B is held constant. Then the reaction rate at two different values of concentration of A is analyzed to determine the order of the reaction with respect to the concentration of A as follows. So we use this expression to determine our exponents alpha and beta, as we'll see on the next slide. So notice in this expression that the concentration of B and the rate constant K are constants in each measurement. Therefore, they cancel when one evaluates the ratio of the measured reaction rates. So in this expression, these two terms will cancel, as well as these two terms. So what you're left with is a ratio of the concentrations of A to the exponent alpha. And if we take the natural logarithm of both sides of our expression, we can then solve for alpha explicitly. So using this equation, the order of the reaction with respect to A is readily determined. Now we can carry out a similar experiment to determine beta, and that can be performed where the concentration of A is held constant and the dependence of the reaction rate on B is measured. Or, if you wish, you can use the original expression, but now that you've solved for alpha, you can determine beta as the only variable that is unknown. Now, there are some disadvantages to this approach. First, one must have a substantial amount of control over the reaction. Specifically, the reactant concentrations need to be controlled and mixed in any proportion desired. Second, one must have a substantial amount of reactants. Running this reaction multiple times would require that we have lots of A and B available to us. And thirdly, reaction rates must be measurable immediately after the initiation of the reaction. This may not be possible if reactants are unstable or the timescale of the reaction of interest is too short. So let's look at the following example, where again we have two reactants A and B giving us a product C. And we're asked to use the following data to determine the order of the reaction with respect to both A and B and determine the rate constant for this reaction. So the initial step in this question is to determine the order of the reaction with respect to A. And we choose to do that because if you look at rows 2 and 3 of our experimental data set, the initial rates are determined at a constant concentration of B. And so the concentrations of A are varied, and that is what is causing a difference in the initial rate. And so if we use the expression that we just described, assuming that concentration of B is held constant, we also know under those conditions the rate constant will also be equivalent. We get this form of our expression. And so by substituting in the initial rate data at the specific concentrations of A, we can simply solve for alpha. And so alpha, after doing the calculation, ends up being 2.02. This is going to round down to an integer 2. Therefore, the order of the reaction with respect to reactant A is 2, or second order. Now let's use this information to determine the order with respect to B. Now I'll note that in our table, there are no sets of data that hold the concentration of A constant and vary the concentration of B. So in order to solve for beta, we need to first determine alpha, and that's what we've done. So we start with our original expression again, and again we can cancel the rate constant because that will be equivalent in both sets of initial rate data. So if we rearrange that expression for terms containing beta, and then take the natural logarithm of both sides as shown, we can solve for beta explicitly. So we substitute in our values from our data table, solve for beta, and we end up with a value of 1.00. Therefore, the order of the reaction with respect to the reactant B is 1, or first order. Now that we've determined alpha and beta for this particular reaction, we can determine the rate constant. Now that we've determined the rate law expression for this reaction, we can use any row from the table to determine the rate constant. And that's done by first rearranging this expression for the rate constant K, inputting the data from one of those rows in our table, and the end result is a rate constant of 3.20 times 10 to the 8, molar minus 2, seconds minus 1, which are the units of our third order reaction. So if you have any questions about determining reaction orders, by all means, please send me an email. Thank you.